Every day, somewhere on the coast of the Netherlands, a machine quietly moves more weight than the Eiffel Tower, before most people have finished their morning coffee. Not with rockets, not with explosions, just steel cables, perfect timing, and mistakes measured in inches. Here's the strange part. By the time a container ship finally reaches the dock, the hardest work is already over. Its arrival was planned weeks ago. Every container already has a destination. Every crane already knows what it will lift, and thousands of decisions have already been made before a single rope touches the pier. So why can arriving just 1 hour too early cost millions of dollars? Why does moving one container sometimes mean moving 100 others first? And how do you keep something the size of a floating skyscraper perfectly balanced while you're taking it apart? To answer those questions, we need to follow a single container through one of the most extraordinary engineering systems humans have ever built. Because modern ports don't just move cargo, they move the global economy. Take a look around you. Your phone, your shoes, the chair you're sitting on, even the coffee in your cup. There's a good chance every one of those things spent part of its life inside a steel container crossing an ocean. But here's what's surprising. Most of us never think about what happens after that ship reaches land. We picture a crane lifting a few containers, some trucks driving away, and that's about it. The reality is far more extraordinary. A modern port isn't just a place where ships unload cargo. It's one of the most precisely coordinated engineering systems on Earth. Thousands of people, hundreds of machines, millions of tons of cargo, all moving through the same space without bringing everything to a standstill. And the margin for error? Much smaller than you'd expect. One delayed ship can throw off dozens of others. One misplaced container can waste hours. One wrong decision can ripple through supply chains on the other side of the world. Which raises an interesting question. How do you build a system capable of moving millions of tons of cargo every single day without descending into complete chaos? The answer begins long before the first crane starts moving. In fact, it begins with a ship that's still far out at sea. Before you can understand how a modern port works, you first have to understand what it's designed to handle. Imagine you're standing on the shoreline. Far in the distance, a ship begins to appear over the horizon. At first, it looks surprisingly small. But as it gets closer, something strange happens. It just keeps getting bigger and bigger, until you realize this isn't just another cargo ship. It's one of the largest moving structures ever built. Some of today's biggest container ships stretch for more than 400 meters, longer than 4 football fields laid end to end. They can carry over 24,000 shipping containers on a single voyage. That's enough cargo to fill thousands of trucks, enough products to stock millions of homes. But here's the part that surprised me. The challenge isn't handling one of these ships. It's handling several of them. At the same time, on any given day, the world's busiest ports are guiding multiple giant vessels into harbor, assigning each one a berth, unloading thousands of containers, loading thousands more, and sending them back out to sea, all without traffic jams, all without collisions, and all while the clock is ticking. Because every extra hour a ship spends waiting at port can cost tens of thousands of dollars. Which means the biggest problem isn't the ship itself. It's making sure that ship arrives at exactly the right moment. And that's where things get really interesting. Because long before a captain can even see the coastline, the port already knows they're coming. You'd think the hardest part begins when a ship reaches the dock. It doesn't. By the time the crew can see the cranes on the horizon, the port has already been preparing for their arrival for days. Sometimes, even weeks. Every large cargo ship continuously broadcasts its position, speed, and direction using a system called the Automatic Identification System, or AIS. That means port operators don't have to guess where a ship is. They can watch it cross entire oceans in real time. But knowing where a ship is isn't the same as knowing when it should arrive. Here's why. Imagine inviting hundreds of guests to a wedding, but the venue only has one entrance. If everyone shows up at exactly the same time, chaos, cars back up, people wait outside, everything falls behind. Now replace those cars with container ships, some carrying more than 20,000 containers and worth hundreds of millions of dollars. That's the challenge modern ports face every single day. Contrary to what most people think, ships can't simply pull into port whenever they arrive. Everything has to line up perfectly. The shipping channel must be clear. The assigned berth has to be available. The cranes have to be ready. The tugboats have to be standing by. The cargo yard must have enough space. The trucks and trains have to be scheduled. And in many ports, even nature gets a vote, because some harbors simply aren't deep enough for fully loaded container ships to enter at low tide. Miss the high tide window, and that ship may have to wait offshore for another 12 hours before there's enough water beneath the hull to enter safely. Think about that. After crossing thousands of kilometers of open ocean, a ship's schedule can be decided by just a few extra feet of water. That's one reason ports around the world have spent billions of dollars dredging their harbors. By digging deeper channels, they allow larger ships to enter more often, reducing delays, increasing capacity, and keeping global trade moving. But even the deepest harbor can't solve every problem, because one late ship doesn't just affect one dock, it can affect an entire port. If one vessel arrives behind schedule, the next ship may have nowhere to berth. The cranes assigned to it sit idle. Trucks begin waiting. Rail schedules shift. Crews work overtime. And before long, a delay that started hundreds of kilometers away has spread through the entire terminal. That's why port operations look less like a parking lot and more like air traffic control. Teams of planners constantly monitor every vessel, adjusting schedules as weather changes, traffic builds, or unexpected problems appear. They're solving a puzzle that's constantly changing. Every decision has consequences. Every minute matters. And every successful arrival is the result of thousands of calculations happening quietly behind the scenes. Eventually, everything falls into place. The tide rises. The berth becomes available. The tugboats move into position. A local harbor pilot climbs aboard. And after weeks of planning, thousands of calculations, and a journey across an ocean, the ship finally reaches the dock. Now comes the part everyone thinks is impossible, lifting thousands of containers off a moving skyscraper, with only centimeters to spare. After days, sometimes even weeks, the ship finally comes to a stop. From a distance, it looks like the hard part is over. It isn't. In fact, everything you've seen so far has simply been preparation, because the moment the first line is tied to the dock, the clock starts ticking. Every hour that ship remains alongside the terminal costs money, not just for the shipping company, but for the port, the trucking companies, the rail operators, and the businesses waiting for their cargo. The sooner the ship can unload, reload, and leave, the sooner it starts making money again. So, how do you unload thousands of containers without bringing the entire port to a standstill? The answer is impossible to miss. Towering above the ship are machines so large they almost look like part of the skyline. Ship-to-shore cranes. These are among the largest moving machines ever built. Some stand more than 100 meters tall, with giant booms stretching across the entire width of a container ship. From the ground, they look almost slow, graceful even. But don't let that fool you. Every movement has been carefully planned. Every second has been measured. Every lift has a destination waiting for it. Here's what surprised me. The cranes aren't designed to lift incredibly heavy things. Construction cranes can often lift far more weight. What makes these machines extraordinary is their precision. Imagine lowering a steel box weighing more than 30 tons from the height of a 30-story building onto a moving ship with only a few centimeters of clearance. Now, imagine doing that over and over and over again, thousands of times, without damaging the cargo, without hitting another container, without stopping the operation. To make that possible, operators rely on cameras, laser guidance systems, sensors, and years of experience. Some of the newest cranes are even partially automated, allowing computers to assist with positioning while human operators supervise the lift. But speed matters just as much as accuracy. A skilled crane can move a container roughly every 90 seconds. That might not sound particularly impressive, until you realize several cranes are usually working on the same ship at once. Together, they create a carefully choreographed rhythm. Lift, move, lower, release, return, again and again. hour after hour, container after container. By the end of the day, thousands of containers have disappeared from the ship, as if by magic. But here's the twist. Lifting the containers turns out to be the easy part, because the real question isn't, can you move a container? It's, where should it go? The answer to that question determines whether the entire port runs smoothly or descends into complete chaos, and that's where an army of robots quietly takes over. You'd think the hardest part is getting a container off the ship. It isn't. The real challenge begins the moment it touches the ground. Think about what just happened. In only a few hours, thousands of containers have been lifted from the deck. Now, every one of them has to go somewhere. Some are leaving by truck, others are heading for a train. Some will wait for another ship, others need to be inspected by customs. And every one of them has a deadline. So here's the question. How do you move thousands of containers across a busy terminal without creating the world's biggest traffic jam? Years ago, the answer was simple. Hundreds of drivers, hundreds of trucks, constant radio communication. Today, many of the world's busiest ports do something completely different. The drivers have disappeared. The moment a container leaves the crane, it's placed onto an automated guided vehicle, or AGV. There's no cab, no steering wheel, no driver. Just a low electric platform quietly carrying a container across the terminal. At first glance, the whole thing looks chaotic. Dozens of vehicles crossing paths, turning in different directions, moving at different speeds. But look closer, and you'll notice something remarkable. None of them hesitate, none of them honk, none of them get stuck, because every movement has already been calculated. Some AGVs navigate using GPS accurate to within a few centimeters. Others rely on laser scanners, onboard cameras, or tiny transponders embedded in the pavement. Every second, they communicate with the terminal's computer system, which constantly adjusts their routes to avoid delays. To a human driver, it would look impossible. To a computer, it's just another optimization problem. Eventually, each vehicle arrives at the storage yard, and that's where another giant machine takes over, the automated stacking crane. Its job sounds almost too easy. Pick up a container, find an empty space, put it down. Done. Except, that's not really its job at all, because putting a container in the wrong place today can create a problem weeks from now. Imagine parking your car in a garage, knowing you won't need it for a month. Now imagine someone parks 50 other cars in front of it. When it's finally time to leave, every one of those cars has to be moved first. That's exactly what ports are trying to avoid. A single misplaced container can force cranes to make dozens of unnecessary lifts, wasting time, using more energy, delaying trucks, and slowing down the entire terminal. So these cranes aren't simply stacking containers wherever they fit. They're following a plan so detailed that before the ship even reached the harbor, someone had already decided exactly where every single container should go. Not a person, software. And that software is solving one of the most complex puzzles in modern engineering. One wrong decision can affect an entire voyage. So, how does it decide where 20,000 containers belong? So how does software decide where 20,000 containers belong? At first, it sounds like a simple game of Tetris. Find an empty space, put the container there, move on to the next one. But that's not how it works. In fact, it's not even close. Here's the part that surprised me. By the time the first crane lifts its first container, the entire ship has already been loaded. Not physically, mathematically. Every container has an assigned position. Every position has a purpose, and every decision affects thousands of others. So what exactly is the software trying to solve? Well, imagine you're packing for a month-long trip, some clothes you'll need tomorrow, others you won't touch for weeks. Some items are incredibly heavy, others are fragile. Some must stay cold, some can't be stored next to certain chemicals. Now imagine packing all of that into one suitcase that someone else will unpack in 6 different countries without ever taking out the wrong item. Sounds impossible. Now replace that suitcase with a ship carrying more than 20,000 containers. Suddenly, you're beginning to understand the challenge. Every container is different. Some weigh over 30 tons. Others are nearly empty. Some are carrying frozen food that must remain connected to electrical power throughout the voyage. Others contain hazardous materials that international regulations require to be stored in very specific locations. And every one of them has a different destination. The software has to consider all of those factors at the same time. Move one heavy container, and the ship's balance changes. Move one refrigerated container, and you may lose access to a power connection. Place hazardous cargo in the wrong location, and you've violated international safety regulations. This isn't just loading cargo. It's solving millions of possible combinations, looking for the one arrangement that keeps the ship safe, keeps the cranes efficient, keeps the schedule on time, and keeps the entire voyage running smoothly. It's one of the largest optimization problems solved every single day. But here's the frightening part. The software isn't just deciding where cargo belongs, it's deciding whether the ship will safely cross an ocean. Because one bad decision might not become a problem until the ship is hundreds of kilometers from land. So, what happens if the software gets it wrong? Imagine placing hundreds of the heaviest containers near the very top of the ship, or loading far more weight on one side than the other. The ship would still float, but it wouldn't float safely. Instead, it could begin to lean. Not dramatically, at least not at first, but even a slight list places enormous stress on the hull. It changes the way the ship moves through the water, and in rough seas, it can make every wave more dangerous than the last. In extreme situations, poor cargo distribution has contributed to structural damage and even the loss of containers during severe storms. That's why every container has two jobs. The first is carrying cargo. The second is helping keep the entire ship balanced. So before a single container is loaded, the software runs thousands of simulations, checking how every decision affects the vessel from front to back, side to side, and from the bottom of the hull to the highest stack on deck. One of the most important calculations engineers monitor is something called the metacentric height. The name sounds complicated. The idea isn't. Think of balancing a broomstick on your hand. If the balance point is wrong, the broom falls over. Ships work in much the same way. The metacentric height tells engineers how the ship will respond when waves push it from side to side. Too little stability, and the ship rolls slowly, struggling to return upright. Too much, and it snaps back so violently that enormous forces travel through the cargo. Neither is ideal. Finding the right balance is critical. Fortunately, modern software can calculate in seconds what once required hours of manual planning. But even perfect balance doesn't solve the biggest challenge, because the software isn't planning for one destination, it's planning for an entire voyage. Think loading a ship is complicated. Unloading it can be even harder. Here's why. A container ship rarely visits just one port. It may stop at 5, 7, or even 10 different ports before completing its journey. That means the first containers that need to come off can't be buried beneath hundreds of others that won't be unloaded until the final stop. Otherwise, the cranes would have to remove containers that aren't even supposed to leave the ship, just to reach the ones that are. Imagine unpacking your suitcase, only to discover the passport you need is buried beneath everything else. Now imagine your suitcase weighs 200,000 tons. Every unnecessary lift wastes time. It keeps cranes busy longer than necessary. It delays trucks waiting below. It slows trains, and it forces ships to remain at the dock longer than planned. In an industry where every hour matters, those extra moves can cost hundreds of thousands of dollars. So the software isn't simply deciding where containers fit, it's planning an entire journey. Before the ship even leaves the harbor, computers have already mapped out where every container will be loaded, where it will be unloaded, and the exact order in which thousands of containers will leave the ship over the next several weeks. It's one of the most remarkable planning problems humans have ever solved. But even the perfect loading plan has one unavoidable flaw. The ship won't weigh the same tomorrow, as it does today. Every container that's removed changes the balance of the entire vessel. So, how do you keep a floating skyscraper perfectly upright, while thousands of tons of its weight are constantly disappearing? Imagine building a skyscraper, then removing entire floors from one side, while expecting the building to stay perfectly upright. It sounds impossible, yet that's exactly what happens every time a container ship is unloaded. With every container, a crane lifts from the deck. The ship becomes a little lighter. Its center of gravity shifts. Its balance changes. Now multiply that by thousands of containers being removed over the course of a single day. You might think the ship would slowly begin to lean, and if nothing were done, it would. Not enough to suddenly capsize, but enough to place enormous stress on the hull, reduce stability, and make every remaining crane lift more dangerous. So how do crews stop that from happening? The answer isn't on the deck. It's hidden deep inside the ship, beneath the containers, beneath the engines, and below the waterline. Inside the hull are enormous ballast tanks capable of holding thousands of tons of seawater. As containers leave the ship, powerful pumps quietly move water between these tanks, or bring in fresh seawater from outside to replace the weight that's disappearing above. The process never stops. While cranes are lifting containers every 90 seconds, the ballast system is constantly recalculating the ship's balance, adjusting, correcting, keeping the vessel level almost minute by minute. Most people watching from the dock never notice. They see cranes moving, trucks driving, containers stacking, but hidden beneath all of it is another operation happening at exactly the same time, one that's just as important. Because without it, the entire unloading operation would become slower, more dangerous, and in some cases, impossible. But here's the twist. The ballast system doesn't just keep the ship balanced. It also has to protect the oceans the ship sails through. For decades, ships pumped seawater into their ballast tanks in one part of the world, then released that same water thousands of kilometers away. At first, nobody thought much about it, until scientists discovered that the water wasn't empty. It carried tiny fish, shellfish, algae, bacteria, even microscopic organisms invisible to the naked eye. In other words, every ballast tank was carrying an entire ecosystem across the planet. When that water was released into a different ocean, some of those species survived. With no natural predators, they spread rapidly, disrupting ecosystems, damaging fisheries, and costing countries billions of dollars. The problem became so serious that the International Maritime Organization introduced strict global rules requiring ships to treat or exchange their ballast water before releasing it. So today, the same system that quietly keeps a 200,000-ton ship upright also helps protect marine ecosystems around the world. It's an engineering solution with a global environmental responsibility. But even a perfectly balanced ship still faces another challenge. Imagine stacking thousands of steel containers, 10 stories high, then sending them into waves powerful enough to move an entire ship. Why don't those containers simply slide into the sea? The answer comes down to a piece of steel, small enough to hold in your hand, yet strong enough to help secure an entire skyscraper at sea. Look at a container ship from a distance, and all you really notice are the containers, thousands of steel boxes stacked one on top of another. But the real heroes are almost invisible. Hidden between those containers, at each of their four corners, are small pieces of steel called twist locks. At first glance, they don't look particularly impressive. They're small, simple, and surprisingly ordinary. So how can something small enough to hold in your hand help secure containers weighing more than 30 tons each? The answer isn't how strong they are, it's how they're used. Every shipping container is designed to carry its weight through its reinforced corner posts. When one container is lowered onto another, the twist lock fits between their corners. With a simple 90-degree turn, it locks both containers together. Do that thousands of times, and separate containers become one giant structure. It's an elegant solution. Simple, reliable, and incredibly effective. But here's where things become interesting. The greatest danger isn't the weight, it's the motion. Out on the open ocean, a ship never sits still. It rolls from side to side. It pitches forward and backward. It twists as waves strike from different directions, and every movement sends enormous forces through the stacks of containers. From the shore, everything looks calm, but inside those stacks, Thousands of tons of steel are constantly pushing and pulling against one another. That's why engineers don't design these systems for calm weather. They design them for the worst storm the ship might ever encounter, because if one twist lock fails, the extra load is transferred to the ones around it. If enough connections are overloaded, an entire stack can become unstable. That's one reason container losses still happen during extreme weather. Not because engineers overlooked something, but because nature sometimes produces forces that push even the best designs to their limits. It's a reminder that no matter how advanced our technology becomes, the ocean is always stronger. Which raises an obvious question. If storms can threaten billions of dollars worth of cargo, why don't ships simply avoid them altogether? As it turns out, that's exactly what they try to do. You might think that once a ship leaves port, the fastest route is simply a straight line to its destination. It isn't. In fact, the shortest route is often the slowest one. Here's why. Imagine you're driving across the country. Your navigation app tells you there's a massive storm directly ahead. You wouldn't drive straight through it. You'd find another route. Container ships do exactly the same thing, except instead of avoiding traffic, they're avoiding waves taller than buildings, hurricane-force winds, and seas powerful enough to twist one of the largest moving structures on Earth. Remember those thousands of containers stacked high above the deck? Every time the ship rolls, every time it pitches, every time a wave slams into its side, those containers experience enormous forces. The greater the movement, the harder the twist locks have to work. The more stress travels through the hull, and the greater the chance of damaged cargo. Or worse. So how do captains know where it's safe to go? The answer is space. Literally. Weather satellites continuously monitor cloud systems, wind speeds, wave heights, ocean currents, and developing storms across the globe. That information is combined with sophisticated weather models capable of predicting conditions days in advance. Specialized weather routing companies then analyze all of that data and recommend the safest and most efficient route. Sometimes the advice surprises people. Instead of sailing straight toward the destination, the ship may travel hundreds of kilometers out of its way. At first, that sounds inefficient. But here's the twist. A longer route often gets the ship there faster, because avoiding rough seas allows the vessel to maintain a higher average speed, burn less fuel, protect the cargo, and stay on schedule. The shortest distance between two ports isn't always a straight line. It's the safest one. But no forecast is perfect. Storms change, winds shift, equipment fails, unexpected situations happen. And when they do, technology can only help so much. Eventually, someone has to make the final decision. After everything you've seen, the software, the automation, the robots, you'd be forgiven for thinking modern ports practically run themselves. They don't. Some of the most important decisions are still made by people. Take a ship approaching a harbor. The captain may have crossed an entire ocean, but there's one person who knows those final few kilometers better than anyone else: the harbor pilot. Just outside the port, a small pilot boat races alongside the moving ship. At exactly the right moment, the pilot climbs aboard, sometimes using nothing more than a rope ladder hanging down the side of a vessel taller than a 10-story building. From that point on, they guide the ship safely into the harbor. Not because the captain lacks experience, but because every port is different. The tides change, the currents shift, sandbars move, the wind behaves differently around every coastline, and local pilots spend years, sometimes decades, learning details that no chart or computer can fully capture. But they're only one part of the human team. High above the terminal, inside operations centers filled with screens, another group of specialists watches every movement across the port. They can see every crane, every truck, every automated vehicle, every ship, and every container. If a crane suddenly stops working, they adjust the schedule. If weather delays an arriving vessel, they reorganize the entire operation. If customs holds a container unexpectedly, the software updates, and the people decide what happens next. It's less like running a construction site, and more like conducting an orchestra. Thousands of moving parts. One performance, no room for mistakes. Here's what surprised me most. Automation hasn't replaced people. It's changed the problems people solve. Machines handle the repetitive work. Humans handle the unexpected. Because no matter how intelligent the software becomes, the real world will always find new ways to surprise it. And once the last container finally leaves the ship, its journey is only half over. You'd think the race ends when the last container leaves the ship. It doesn't. In many ways, it's only just beginning. A container sitting in the port isn't doing its job. It isn't earning money. It isn't delivering products. It's simply waiting. And in modern logistics, waiting is expensive. So the moment a container touches the ground, another countdown begins. Where does it go next? That depends entirely on what's inside. Some containers are loaded directly onto waiting trucks, delivering goods to nearby warehouses, factories, and distribution centers. Others never touch a road. Instead, giant cranes transfer them straight from the terminal onto freight trains, stretching for hundreds of meters. In some of the world's busiest ports, a container can leave a ship, be placed onto a train, and begin crossing an entire country in less than an hour. Think about that. Something that spent weeks crossing an ocean can begin another journey almost immediately. No warehouses, no long delays, just one transportation network handing cargo to another. And none of it happens by accident. Every truck arrives at a scheduled time. Every train has a reserved loading window. Every container already knows exactly where it's going next. Because a modern port isn't simply unloading ships. It's connecting the world's transportation systems. Ships, railways, highways, warehouses, distribution centers, all operating like one enormous machine. And here's what makes that machine so remarkable. Every part depends on every other part. If a train arrives late, containers stay in the yard longer. Those containers occupy valuable space. That slows the cranes. Ships spend more time waiting at the dock. And suddenly, a delay hundreds of kilometers inland has reached all the way back to the harbor. One small problem, thousands of consequences. Which raises another question. How does anyone keep track of millions of containers moving through a system this complex? The answer isn't another machine. It's information. Walk through a modern port, and you'll notice the obvious things. The ships, the cranes, the trucks, the endless stacks of containers. But none of those are actually in charge. Behind every movement is a digital system making millions of decisions every single day. Think about it. At any given moment, one port may be responsible for hundreds of thousands of containers. Some have just arrived. Others are waiting for customs. Some are heading for trains. Others are about to begin another voyage across the ocean. So, how do you keep track of all of them without losing a single one? The answer is data. Every container has a unique identification number. As it moves through the terminal, scanners, cameras, RFID systems, and sensors continuously update its location. That information flows into something called a terminal operating system. Think of it as the brain of the entire port. It knows where every container is, where it's going, which crane should move it, which truck should collect it, and exactly when each step should happen. The moment something changes, the entire system adapts. If a ship arrives late, the schedule changes. If a crane develops a fault, its workload is reassigned. If weather delays one operation, hundreds of others are automatically adjusted, and ports are becoming even smarter. Artificial intelligence is beginning to predict equipment failures before they happen. Instead of waiting for a crane to break down, sensors monitor vibration, temperature, power consumption, and thousands of other data points. When something doesn't look right, engineers receive a warning before the failure ever occurs. Drones inspect equipment without shutting down operations. Digital twins allow entire terminals to be tested inside computers before changes are made in the real world. Even paperwork is disappearing, replaced by digital systems that move information almost as quickly as the cargo itself. Here's the part that surprised me most. For decades, ports became faster by building bigger cranes, larger ships, and deeper harbors. Today, some of the biggest improvements don't come from building anything new. They come from making smarter decisions with better information, which means the future of ports may not be built from more steel, but from more intelligence. And when you step back and look at the entire system, you begin to realize something remarkable. The next time a package arrives at your door, take a second to think about the journey it made. Long before it reached your street, it crossed an ocean aboard one of the largest moving machines ever built. It traveled through storms, passed beneath towering cranes, moved across a terminal by driverless vehicles, was tracked by software that knew its location every second of its journey, and was carefully transferred from ships to trains to trucks until it was one step closer to you. Think about how many things had to go right. The ship had to arrive on time. The berth had to be available. The cranes had to work flawlessly. The cargo had to be loaded in exactly the right order. Thousands of containers had to move with incredible precision, without bringing the entire system to a halt. And behind it all, millions of calculations, thousands of skilled people, and some of the world's most advanced machines work together to make it happen. That's what makes modern ports so remarkable. They're not simply places where cargo changes hands. They're the beating heart of global trade, 24 hours a day, 7 days a week, quietly connecting factories, railways, warehouses, businesses, and billions of people around the world. When everything works perfectly, nobody notices. You click, buy now. A few days later, a package appears at your front door. It feels effortless, but now you know the incredible engineering hidden behind that ordinary moment. Perhaps that's the greatest achievement of all. The world's most important systems are often the ones we never see. But here's something we haven't answered yet. The container has reached the port. So, how does your package make the final journey to your doorstep? Because getting a container across an ocean is only half the story. Getting one small package to the right house, on the right street, at exactly the right time, is an engineering challenge all by itself. In the next video, we're following that journey, from giant container ports, to massive warehouses, to high-speed sorting centers, to the delivery van that stops outside your home. If you've ever wondered how millions of online orders arrive at the right address every single day, click the video on your screen now, how online orders reach your door. Once you see what happens behind the scenes, you'll never look at a simple delivery the same way again.